Hello students, welcome you all to the discussion on the introduction part of turbo machines. Today we are coming to the end of this particular session, that is introduction to turbo machines. In today's class, we will be discussing regarding effect of Reynolds number in turbo machines. And for this effect of Reynolds number, I have referred on the equation known as Moody's equation, which will be used in solving the problems, especially when you're determining the power of the prototype. And one problem related to the determination of power of a prototype using the efficiency of Moody's equation. So in today's class, we'll be discussing these terms. So if you have any queries, right now on the screen, you can see my email IDs, two email IDs, as well as my mobile number is a WhatsApp number. You can send me an email or message to the WhatsApp also, so that I can solve your queries. So for further more updates, you can subscribe to my YouTube channel, where the updated videos you can get to know when they have been uploaded in the YouTube. So now we shall begin with the discussion of today's session as we move further. So the one concept we had left behind there was the discussion of the effect of Reynolds number in the turbo machines. So you know that the Reynolds number is nothing but it is when a flow is occurring through a pipe, or for a pipe flow, you can say that the Reynolds number is given by this following equation. Sorry, for a pipe flow, Reynolds number, it is given by this particular equation, that is RE is equal to rho into VD by mu, or you can write it as PD by mu also. So where V is the velocity, mean velocity of the fluid which is flowing through a pipe having a diameter D, and also you know that this particular Reynolds number, it is affected by the means of the inertia force and as well as some viscous force also. So in very simple words, whenever the flow occurs through a pipe, we are very much interested to know whether it is a laminar flow or a turbulent flow. So the Reynolds number, it is nothing but it is the ratio of the inertial force to the viscous force. We call it as the ratio of inertial force to the viscous force, the Reynolds number. So in case of a particular flow, if the viscous effects are more than the inertia effect, then automatically the Reynolds number is less than 2000. So if the Reynolds number is less than 2000, the type of flow we call it as a laminar flow. If the vice versa happens, that is the inertial effects are more than the viscous effects, then the Reynolds number changes to value more than 4000, and that time the flow is nothing but it is known as a turbulent flow. Already you have learned this in your previous classes, but just I am briefing you here. So in turbo machines, when the fluids are flowing along with this viscous forces, we need to consider again some of the additional losses, that is the losses which may occur due to the shocks at the entry level, or with the turbulence impact, and even there will be some leakage also. Why does this happen here? It happens here because the fluids which we are especially using the turbo machines, they're having a low viscosity, or we call them as low viscous fluids. That is, they may be in the form of fluid you use, maybe air, it may be steam, water, or any light oils whose viscosity is very, very less. Therefore, obviously what happens, we don't get laminar flow, always it will be turbulent flow in nature itself. So when this is going to occur, then we can say that there is a friction factor which is dependent mainly upon the relative roughness, and which becomes more important, especially for, and this relative reference becomes more constant, especially for the turbulent case of flow, where for a turbulent case of flow, when the flow is turbulent in nature. Therefore, when we are studying with respect to a model and prototype, especially with the model and prototype studies, the surfaces of both, especially of the model and prototype studies, they will be having the same relative roughness. And the effect of this Reynolds number on this relative roughness, it may or may not be significant. That is the reason that we are very much, it becomes very much difficult to measure the average value of roughness. Hence, for all these reasons, a mean float factor was being. Therefore, that is the reason that when it becomes very much difficult to measure the average values of the roughness, and therefore it is an unknown factor. That was the reason that Moody developed some of the values using conducting some experiments, and he plotted the values of friction factor versus Reynolds number, where it would represent the friction factor based upon what? The relative roughness. It was representing based upon the relative roughness itself. So basically, for a model and prototype, both the surface they have their relative roughness. Both the surfaces they have their relative roughnesses, and automatically the effect of Reynolds number it may change or may not be significant depending upon the degree of roughness. Therefore, in order to accommodate all these conditions, the hydro turbines, the prototypes which we are using, they are having a low relative roughness, and this is because of its larger size, and the model has a smoother surface. And because of all these dissimilarities, then and the dissimilarities of the surface model roughness, the model similarity laws, they were need to be corrected with the help of Reynolds number of dependency, by the Reynolds number of dependency we call it. That is, because of all these dissimilarities of surface roughness, the model similarity laws, they need to be corrected with the help of the Reynolds number dependency. That was the reason that when the machines were using the fluids which are having low viscosities or lighter fluids, we were neglecting their viscous fluids. Why? Because you know that the air, water, or steam, or the oils which are having lesser viscosities, as the viscosities are very, very less, they can be neglected. But the important thing was the efficiency of these particular fluids when they pass through those machines. We need to consider those efficiencies, especially during the varying load conditions and their sizes. So depending upon the efficiency, it would change completely depending upon different load conditions as well as different varying sizes. Keeping this into mind, Moody developed a chart and he suggested an equation to which you can determine the turbine efficiencies by conducting some experiments with the help of an geometrically similar models. And that particular equation, you call it as the Moody's equation, which you can see here right now here, where you can see that the efficiency of a prototype eta P is equal to 1 minus whole bracket 1 minus eta M into diameter of the prototype, diameter of the model to the diameter of the prototype to the power of 0.2 to the power of 0.2. So all this together is nothing but it is a Moody's equation, where eta P is nothing but efficiency of the prototype having a diameter dP. Eta M is the efficiency of the model of diameter dm. Please do remember this equation for efficiency of the prototype, because in the problems when he has asked to calculate the power of a prototype considering the Moody's equation, then compulsorily you need to find out the value of eta P using this particular equation, So this has to be kept in your mind. So this was the reason that Moody developed this particular equation. So many times in the examination, this question may be asked regarding the effect of Reynolds number. So you need to highlight these points and say what is the purpose of using this particular equation, especially for calculating the power of prototype in turbo machines. Now, using this particular concept regarding the Moody's equation, let us discuss one problem here, which will help you to understand how it plays a role in calculating the power of an prototype. So already this question yesterday I have discussed. Just once again, I am going to brief it here. So you can see here that a test on a turbo machine which you are seeing here right now, it is having this much diameter of around 1.25 meter in diameter. It is a height of 30 meters, which can give the following results. And the power developed is how much here? 736 kilowatt. Speed is 180 RPM. Discharge is 2.7 meter cube per second. You need to find the diameter, speed, and discharge of Werner, which is to be operated at 45 meters head with the power of 1470 kilowatt, having the same efficiency. So you need to find the specific speed of both the turbines. So if you analyze the data once more, just I'm going to highlight here. Already he has given the head of a turbo machine, the first machine, that is H1. Then he has given the diameter of the first turbo machine as D1. He has given power of a first turbo machine as P1. Then he has given speed of first turbo machine as n1 and discharge as 2.7 for the first machine. These are with respect to the first turbo machine. You need to find the diameter for the second machine, that is d2. It is the unknown factor. Then this you need to be found out. Similarly, speed n2, this has to be estimated. Then you have to find out discharge of a runner, that is q2. Then you need to find out these things. They are operated at a head of how much? 45 meter. So the second turbo machine is operated at a head of 45 meter with a power of how much? 1472 kilowatt P2. But the condition he has said that both these machines, they are having the same efficiency. So what does it mean? It means mathematically eta 1 is equal to eta 2. And apart from it, he has also to find out the specific speed of the machines. That is this particular thing. He has also to find out specific speed of the machine. These are the things you need to find out. It is asked in the year December 2018, January 2019. So let us go to the solution part of this particular problem. I have noted down the given things. Coming to the solution part. So initially what I will do is I will go with finding the specific speed of the equation. So specific speed is ns is equal to n1 root of p1 h1 to the power of 5 by 4. All the things are already given in the question. h1 is available, p1 is given, even n1 is given. So once I substitute the values, I get the specific speed as 69.55. Then I can use this same value and I can find out the speed n2 using the same specific speed equation. So using the same specific speed equation for second turbine, I get it as this equation. Ns is equal to n2 root of p2 by s2 to the power of 5 by 4. Or this I can relate it as n2 1472 by 45 to the power of 5 by 4, or n2 value is this much. So once you get the value of n2, you need to find the value of discharge. So you need to find the value of using this particular head coefficient equation. So once I use this head coefficient equation, gh1 by n1 square d1 square is equal to gh2 divided by n2 square d2 square. You go on substituting the values. So once you substitute the values, I get the value of d2 as 1.304 meter. d2 is over. Then the next important thing is regarding, once you have calculated the value of d2, the next term which we are left with is discharge, which is happening at second turbo machine q2. So to find that one, you can use you are following a flow coefficient equation. You can use a flow coefficient equation, that is q1 divided by n1 d1 to the power of 3 is equal to q2 divided by n2 d to the power of 3. So already you know these things. N1 you know, D1 you know, N2 you have calculated, D2 you have calculated, Q1 is given. So unknown factor Q2 you can calculate using this particular equation. So let us see how we are going to get now the value of Q2. So using the same flow coefficient equation which I have discussed, I will substitute the values, and the Q2 value which I am going to get is 3.306 meter cube per second. It is So in this particular fashion, we get the value of Q2 as 3.306 meter cube per second. Similarly, let us see another one problem where we can use the Moody's equation for calculating the efficiency of a prototype. So the next question we will be seeing regarding this particular turbine. The question given is, he says there is a Francis turbine model which is built to a scale of 1:10. The data for this model is power with 4 kilowatt, n is equal to 2500 rpm, h is equal to 2 meters. Then he says the prototype h is equal to 6 meter. Assuming that the overall efficiency of the model is 60%, calculate speed of the prototype, power of the prototype, use Moody's equation. So in this problem, he has asked to find out speed of the prototype as well as power of the prototype, and the power to be calculated using the Moody's equation. So if you analyze the data given in this problem one by one, if you go step by step, let us start with this particular thing. He says there is a Francis turbine model. There is a model which is built on the scale of 1:10. Scale in the sense it is the size, or you can say that it is a ratio of diameters. So that is diameter ratios. We need to be very familiar. Is it with model to prototype or prototype to model? So here initially I said this is built with respect to a model. So it becomes dm by dp, and its ratio he has said it as 1/10. This is the particular scale ratio. It is built for the model with the power of 4 kilowatt, that is PM. Then he has said the speed, its value is Nm, and he has said it is as head of this model as how much? 2 meters. Then the next sentence he says the prototype head. He has said the prototype head. So the prototype head at this one, it is represented as HP. It is represented as HP. And the next sentence he has said that assume that we need to assume that the overall efficiency, he next says that we need to assume the overall efficiency, and this overall efficiency which you are seeing right now here as given in the question, it states that the overall efficiency of the model as 60%. He says the overall efficiency of the model as 60%. So he's saying with respect to the particular model itself, which means the overall efficiency of the model is 60%, which means eta m value it is 60%. And what he has to find out, he has asked us to calculate speed of the prototype, that is NP, and he has asked us to calculate even the power of the prototype, that is this particular thing, that is power P. He has asked us to find out these things. These are the things which are asked in the problem. So let us start the solution step by step. So as I have shown these things, I will be highlighting the things right now here as you go and write on the given things one by one. Given things, as I told you, it is respect to the model to prototype scale ratio, that is dm by dp is equal to 1/10. The given things, solution. So we'll start with the solution part. So initially I am going to calculate the specific speed of a model machine using this equation. Ns is equal to nm square root of pm by hm to the power of 5/4. So now what happens? The value of specific speed, it is nothing but 2943.1555. This is the value of specific speed. Using the same value with the value of HP, then we move on to the next part. That is, we got to calculate the head coefficient using our head coefficient equation. So in this head coefficient equation, we find out the value of the things which are given in the question. Substitute the values and get the value of NP. We substitute the value of NP here. We need to find the value of NP here. We substitute the values of NM, HP by HM, then DM by VP. Already the scale is given to us. Once we substitute the values on simplification, we get the value of NP as how much? 606.217 RPM. Speed of the prototype is calculated, the first thing. The second thing what he has asked is power of the prototype. So generally when we are writing our power equation, how do we write our power equation? We write it in this form. The power of a prototype as power equation as P is equal to rho G Q H efficiency term. So with respect to prototype, power PP, QP, HP, and efficiency prototype as eta P, right? We need to calculate this one now. So how we need to calculate? Using our Moody's equation, eta P is equal to 1 minus eta m into dm by dp into dm by dp, that is dm by dp whole raised to 0.2. Using this equation, we need to calculate the efficiency of a prototype. Now we shall use this Moody's equation. So I have written this Moody's equation. I substitute the values here and the efficiency of prototype, I get it as 0.7476. Once I get this efficiency of prototype, now I need to find the power of prototype. So what I will do here now is I will take the ratios of the power of the prototype equation to the power of the module equation. So sorry, model equation. Then I simplify. So what I am going to do right now is I write it as power of the prototype PP is equal to rho G Q P H P eta P. This is the power equation. This I am going to equate it with respect of the model PM is equal to rho G QM HM eta M. So these terms gets cancelled. Remaining all values you have, you just go on substituting and you can get the value of power of a prototype. So I use this equation, substitute the values, and one more important thing here is we don't know the value of QP by QH. Sorry, we don't know the value of QP by QM. So for this, you can make use of your flow coefficient term. You can make use of flow coefficient equation. So what is our flow coefficient equation? You can write it as QP by NP dP cube is equal to QM by NM dm cube. We need for what? We need for QP by QM. So what I can write this one? I can write it as QP by QM is equal to QP by QM is equal to NP by NM into dP by dm whole to the power of cube. If you have all the values, you substitute them, you will get the resulting equation. So the same step we are going to do now. Using the flow coefficient equation, I am substituting this equation number 2 in equation number 1. Once I substitute, I get equation 1 as this form. I will substitute the values, you can see here, and after substituting the values and simplification, I get the value of power PS 2589.75 kilowatt. There are some more problems of this kind which you can see here in the next slide. You can see here these problems. You can take this as your homework, solve these problems which they have been asked in the previous YouTube question papers, and send the answers to my email ID, which you can have seen on the first slide itself. So if you have any doubts, you can send me an email or through the email IDs which I have kept on the first slide, as well as send me an WhatsApp also. So try to solve these problems which they have been asked in the previous YouTube question paper, such that you become familiar with these particular problems. So now this ends the discussion of part 1, introduction to turbo machines, in module number 1. In next session, we'll be beginning with the new particular task, that is from module number 2 regarding energy transfer, how it is going to occur in turbo machines. So today we shall stop here, students.